Thank you. Hello, everyone. So I'm going to be talking about a framework that we've been developing at EPFL. So this is the first slide, the default slide offered by Keynote, and I found it fitting like this because my talk is about quasi-quotation, which is a form of quotation. So everyone knows quotation, right? So it puts some text between two quotation marks, and then it's interpreted as a list of characters. Now, quasi-quotation is when you leave holes in this quotation, so you can escape holes using the dollar sign, usually. And so these holes will be filled in later with whatever value happens to go there. So here, this quasi-quote in the context where name equals Jack is equivalent to all work in the play makes Jack a dull boy. So this is the syntax in Scala, right? So it's the same thing, and the S at the beginning of the quotation is to indicate that we're doing a quasi-quote and not just a normal quote. Now, what we're interested in here is to quote code fragments, not strings of characters. So, for example, let's say we have a piece of code like this. As you know, it's equivalent to this. This is just some random piece of code that you may find in Scala. And so you can represent it using an abstract syntax tree. And in Scala, it looks like that, right? So you can represent the explicit structure of the code using AST nodes. And well, it's not very nice because it's very verbose and hard to read. Not ideal. So for this, in Scala, you have reflection quasi-quotes. So it's quasi-quotes that are used to quote code. And the prefix is not S anymore, it's Q. And that indicates that you're not quoting a string of characters, but really an AST. So this is how you would express the same thing in a more concise way. Now, you can use this kind of quasi-quotes in pattern matching, and this way you can define macros that handle pieces of code, such as this macro, this example, which is a macro that swaps two variables A and B. So it introduces a temporary variable. It matches the call site of the macro, which is of the form swap, and two pieces of code that we extract as A and B. And then we introduce a binding for B, for the value of B. We put the value of A in B, and we put the old value of B in A. So very simple macro using quasi-quotes. It's very nice, concise. So it's a valuable tool for metaprogramming. I think most people agree with this by now. So there are some problems with the quasi-quotes offered by Scala by default. They're not statically typed, so you can write anything that is valid syntactically, and it's going to compile, and it's going to generate the code, and only after you've generated the code and you try to type check it, will it fail to compile the program. You also have what is called hygiene problems, in the sense that take the swap macro that we saw earlier. If you happen to have a variable already named temp in the original program, you're gonna expand the macro. If you remember, it introduced its own temp binding, and this binding will interfere with the original binding. So you will get a program that is invalid just because of a name clash. You have scope extrusion, so you can take pieces of code out of their context, and so you end up with programs that have unbound variables that will fail to compile again. And so there's another aspect of hygiene, which is when you try to refer to symbols, using their name, such as math.po, which does the power of 2, in this case, for some exponent. This math name might already be defined by the user, and so you're going to refer to the wrong to the wrong symbol. If you're trying to generate this code and insert it in some context where math is already defined, it's not going to have the semantics that you expected. And so, Scala Quasi-Quotes are just one flavor of quasi-quotes that are out there. It's of the untyped family, similar to Lisp, the basic template high-scale implementation, Stratego, and they support pattern matching, as we saw, and they have almost no guarantee. So when you compile your program, you don't know if they're going to do the right thing, just that it's valid syntax. But you have also, there has also been the statically typed quasi-quote flavor that you can find in Meta or Camel, or the typed version of template high scale. So these are better in the sense that they are type checked at the same time as the meta program, and they don't have hygiene problems usually, but the problem is that they're purely generative, and by that I mean that you cannot pattern match on code. You can always generate code and compose code together, code fragments together, but using quasi-quotation, but you cannot inspect the code that already exists, which is a pretty big limitation when you're doing meta-programming. So what about Squid quasi-quotes? So Squid is our framework. It's a Scala framework that uses macros, but that doesn't change the compiler. You don't need a compiler plugin for type-safe programming. So the Squid quasi-quotes are statically typed, hygienic, and they support pattern matching. And additionally, something that hasn't been seen before, they are reusable in the sense that you can make them manipulate programs expressed in different intermediate representations. For example, the Scala quasi-quotes only manipulate the Scala abstract syntax trees from the reflection API, from the Scala reflection API, and Squid quasi-quotes can be used to manipulate any kind of IR, including the Scala reflection intermediate representation. So, what I mean by reusable exactly is you can have your own user-defined IRs, such as static single assignment, SSA, ANF, CPS, continuation passing style, this kind of stuff. And you can even, if you want, if you already have an embedded DSL, deeply embedded DSL in Scala, you can bind Squid to use that its intermediate representation. We're going to see more in detail later. So one nice thing with static typing is that, for example, it disregards, it type checks the code, inserts all the types explicitly, inserts all the implicit parameters explicitly. So this piece of code is really equivalent to the full explicit version, so, but you don't have to write the full explicit version. It's already inferred for you, right? So if you don't know, in Scala, the list.map function uses implicit can build from evidence. It's not relevant, but you just have to see that there's an implicit parameter that is inferred. Additionally, thanks to the fact that you can extend your own intermediate representations, it means that you can have more normalization, and you can encode the fact that these two pieces of code are equivalent. You can encode the fact that addition is commutative. So let's see a demo. So just a very basic demo. This expresses a piece of code. So for now, disregard the fact that this says IR of double NE. This is equivalent to code of double. The any parameter expresses the fact that it's valid in any context, but that's not the subject of this talk. And so you can give a name to that piece of code, and then create bigger pieces of code, such as this. Right. Right. Okay. So yeah, let's move forward for now. Pattern matching. How does it work in Squid? So it works in a similar way. The syntax is very similar. And so this is an example of a program that takes a term T of type code of T. And if it's of the form a call to math.pow with exponent 2, then it rewrites it to a simple multiplication. And so here, again, is hygienic, so math.pow is not going to conflict with other symbols or stuff like that. You have type parametric matching, because since things are type checked, you need to handle types a bit differently in patterns. So, for example, you can define type preserving rewrite rules, where the Scala compiler will check that the term that you rewrite has the same type as the pattern that you matched, as here. So here we're matching a singleton list from which we take the head, and we can rewrite it directly to just the element of the list. Now, in Scala, you have problems usually when you try to encode these kind of things using abstract syntax trees and generalized algebraic data types, because usually Scala has trouble understanding that the T that you're matching is really the same as the T of the term that we have above, T colon code of T. But Squid provides ways to make Scala understand that small t that you extract and capital T are the same, as long as you do as long as you ascribe the term inside the quasi-quotes. Squid will do the necessary to make it type check and to see that the types are the same. So how do we handle bindings, which is a very tricky question in metaprogramming? One very important thing to see is that we have interoperability between a function that is expressed as one piece of code and between a metaprogram that takes a piece of code and generates another piece of code as a result. So as here, you can see that the first expression is a program that represents the function, whereas the second expression is a program that generates another program. And so the types are different, but we can very easily move between one and the other. And so this allows us to do interesting things, such as here's a pattern where we're matching a binding called X, and we're extracting the body in which this binding is used, so anything that happens after the binding. And so this syntax extracts body as a term of type code int to int, and whenever you pass it a code of int, it will return to you the original body in the original program, but where all references to X have been substituted with whatever you have passed. And so this means that basically the names of bound variables doesn't matter, and this helps ensuring hygiene. So the converse operation is to insert a piece of code, a code of int to code of int. You can insert it as if it was a code of int to int. And this way, you can, for example, if you have a function foo that does some processing on some variable or some piece of code, you can insert that function. So actually, I could have not written this eta expanded form. I could have just written foo here, but here is clear what happens. it's inserted. The function foo is basically inserted and processes the actual binding that is inside the quasi-quote. And so, as an example, let's see how an ANF transformer works. So what is ANF? The A-normal form is a representation of programs where all non-trivial expressions are let bound. So in this in the example of A plus B plus C, it's not a term in ANF form. First, you have to make it in ANF form, you have to bind the A plus B sub-expression, and then you have to bind the result plus C. So that's what we see on the right-hand side. Let bindings are not nested in ANF, so it's pretty straightforward transformation. And whenever there's branches, such as if then else, you use continuations basically as join points at the end of each branch. So instead of taking the result of a branch expression and using it in the rest of the program, here adding one to it, instead of doing that, we define a continuation K that represents the rest of the program, and then we use the branch structure as an entail position so that it's not it's not nested anymore. And so what does it look like using Squid? So I don't know if you can see, it's a little small. Let's see how to define a function called toANF that takes a term of type code of T and returns a term of type code of T because ANF doesn't change the type. It uses a helper function called rec that additionally takes a continuation K, so that's the standard way to do ANF transformation. It facilitates the way you process the program. This recursive function proceeds by pattern matching on the term. So let's see what happens if we have a constant. If we have a constant, all we have to do is let bind it to some value C and call the continuation. And in our case, if our whole program is a constant, then we're just going to end up with the let binding of that constant directly returned because the K that we have passed in the top level function is the identity. So it's just going to return C as is. So there's more complicated cases. If you have something that is already let bound, you're going to recurse inside the bound value and introduce all the necessary let bindings on the way, and then recurse on the body. So it looks like that. The detailed syntax doesn't matter too much. Here's how you do lambda abstraction. So it's similar. I'm not going to go into the details, but the point is that it can be done in a type-safe way and hygienic way. So in the end, we have a ANF transformation that is very concise. So it's basically the same size as the original ANF transformation, but is statically typed and hygienic. So in the original implementation, they had to use gensim, which is a way to generate fresh variable names in order not to confuse bindings. But here it's automatically done. So for example, this program that you pass to ANF, it's expressed not using a quasi-quote, but using a block of code, which is equivalent. IR of block of code is the same as a quasi-quote code something. And so you can see that it rewrites all the expressions, let binding them, introducing a join, and it doesn't confuse the bindings. You see that every constant has its own name automatically generated, although in the program, you only use C in the case of const. Okay. In order to have reusability, what we have is that a Squid quasi-quote expands into code that refers to an object algebra interface, and that interface basically says how to interpret UIR, so how to interpret reifying a constant expression, method application, how to do pattern matching, things like this. And Squid can be used, this is an experimental thing we have in the repo, it can be used to as an alternative to Scala macros, so because Scala macros use Scala Quasi-Quotes, they're not hygienic, they're not type safe, pretty error prone. So we have a macro def annotation that allows you to write easier macros, basically. So Squid offers practical metaprogramming quasi-quotes, type safe and hygienic. Squid doesn't modify the compiler, which is one novelty of the implementation. It's just based on white box macros, basically. And they're reusable, which is also a novelty, and they can be used as an alternative to the current Scala macros. Thank you.
Thank you for your talk. In Haskell also we worked on quoted DSLs with Phil Wadler. There we needed to have normalization. You mentioned normalization, but you didn't cover that. Can you talk about normalization? How do you do that? And
all right, so there's several ways to do it. You can do it at the IR level, intermediate representation level, where so the underlying implementation of UIR that implements the object algebra interface, which is also called finality address. Your implementation of the IR keeps terms in a normalized form. So, for example, as a graph of nodes, right, or as ANF. Do you see what I mean?
Sure, but ANF conversion doesn't do beta reduction or committing conversions. And
well, you can make it do that, right?
So you have a layer on top of this that does that. So basically, every instance of this interface is going to get a normal form.
No, it completely depends on how you implement this interface.
So you have a different function that takes this one as output and produces this same thing as output, but in a normal form.
So you can also, no, I think we're not talking about the same thing.
Okay.
But the other way I was about to say to do normalization is just to process programs using functions such as this one, right? So in this case, it puts programs in a normal form.
Yeah.
And you can have a way to automatically apply this transformation as you go, as you construct programs. That's another way to do it. So either you do it.
Function that does that. Okay. Okay. Thank you.
Yeah.
Sounds like there will be some offline discussion.
Yeah.
I was wondering whether you can say more about the implementation. So you do hygiene on top of the usual macro system. So I suppose you do some sort of gen sim yourself. And
Yeah, right. So the intermediate representation has its own notion of bound symbol that is not nominal. It uses basically an equivalent of gensim, but the point is that you don't see that the quasi-quote interface completely hides those details, and you can use names in the quasi-quote interface, as in here, and get gensim for free, basically.
Just a follow-up question. Does this also solve this math.pow problem that you mentioned?
So we can see it here. Whenever I do something like this, you can see that it fully resolves the name of the symbol that you're referring to. And so there's no possibility of colliding with another name called math, right?
Okay, cool. Thank you.
Yeah.
I believe you mentioned this was implemented using the white box macros, right?
Yeah. Mm-hmm.
So, as far as I know, the macros for Dottie are planned to be black box based. Is this what essentially around white box macros are necessary, or are there any plans in terms of being able to port this to Dotty?
So we need white box macros because the code that's expressed between the quotation marks, the Scala compiler has no way of knowing what it represents in the macro itself. We have to parse it and type check it using the Scala compiler, and then it means that you don't have the type before you do that, and so the result of the macro expansion has the actual precise type that you need. So we could use a compiler plugin to do the same thing, but it would be more annoying. But there's a possibility, and so there are discussions currently about what parts of macros should be carried over to Dotty, and there's a lot of people who use white box macros for similar use cases, and I hope they will survive the transition.